Log on, tune in, find out. Another good idea from Cambridge.
The fourth lecture by Emmanuel Candes.
Still 3 a.m. in California. Okay. All right, so today we're going to do a bit of mathematics, and we're going to talk about ideas for proving this incoherent sampling theorem. And this afternoon we're going to talk about compressed sensing with noise. I think I'm going to change lecture 7 somewhat. I think it's better perhaps to stay within the theme of these lectures and tell you about recent development at the boundary between sparsity and low-rank modeling, rather than try to introduce a whole new topic on large-scale convex optimization. I'll say some things about convex optimization, but my plan at the moment is to change slightly the tomorrow's lecture's topic. And then on Friday we'll see applications and hardware and implementations of compressed sensing ideas. In particular, we'll explain what this chip is doing. Okay. All right, so the agenda for today is I would like to start with a numerical interlude to just maybe lots of people come after the lectures asking me questions, and I just want to show you some numerics that perhaps answer some of these questions. But then really the bulk of this lecture is going to be dedicated to this incoherent sampling theorem. We're going to talk about eigenvalues of random submatrices. We're going to talk about large deviation inequalities for matrix-valued random variables. And then we're going to talk about a very nice technique called the golfing scheme, which I happen to like a lot. Okay, so before I get started, I want to start with a numerical interlude. And again, the idea is to kind of try to respond numerically, at least, to some of the questions that have been raised. So, okay, so first of all, what I'm going to do is, does everybody know MATLAB or not? Not everybody. So people will, I mean, it's code that I'm happy to post online. And so I'm going to set a random seed. Oops, I hope that this is working. Well, I had lots of things prepared, so. Okay, let's see. Okay. Okay, so this my issue is that, okay, maybe I should do this, sorry. The MathWorks is really highly problematic. They want to check my license all the time. If I'm connected to the Cambridge network, it would not accept it. I have to VPN to home to actually be able to do something. Okay, now we're in check. Okay, so now what I'm going to do is I'm going to generate a random matrix of size 256 by 512. I'm going to put I'm going to make a sparse vector which has a sparsity which is S equals M over 4, and I'm going to solve with L1. And I told you many times during these lectures that we should be in shape that if the oversampling factor is roughly 4 times the number of measurements, 4 times the sparsity level, L1 will work in general. And what I'm going to use here is I'm going to use some very nice code developed by Stephen Boyd and Michael Grant from from Stanford, who basically wrote wrappers to actually write down in MATLAB optimization problem the way you would write them on paper. And so what I'm going to do is I'm going to minimize the norm of x, the one norm of x subject to x equals b, and then I'm going to show you the result. Okay, so I'm going to run this. All right. And what is this? It's not what I want. Okay, so maybe I'm going to go here. Okay, so I'm going to do the same thing. I'm going to say the same minimization problem. Now, of course, there's things. And what we see that in blue, you see the original signal. In red, in the red dots, you see the recovery, and the recovery is completely exact. Okay? Is the picture clear? Right? In blue, we see the original signal. In red, we see the decoded signal by L1 minimization, and there is no discrepancy. Okay. We just see the red because the red, all the zero values, the red is exactly on top of the blue, so the red overlays with the blue, and so you don't get to see the blue because you're exactly on top. Okay. All right. Okay, so now what happens if we reduce the sampling rate? Okay, so I can go back here and I can say, well, suppose that the sparsity increases so that now the number of equations per really non-zero unknowns is not 4 but 2.5. Okay, so I'm going to now just the only thing I'm going to do is I'm going to increase the sparsity level. So now I'm not close enough for comfort. Okay, so I'm going to run this thing. Okay, I'm going to minimize the optimization problem again. And what do we see? We see that the recovery is not exact anymore. I don't have enough equations per degrees of freedom. But it's not dramatic either. Right? So what we see is you see the guesses. So you see this is a red guess, a blue dot. It's kind of exactly on the money. And then you see that the large guys, you see red dots nearby. We're not too far off. And of course, the guys near zero, we're not doing too good. But you can see numerically that the numerical error, that the relative error is not that large. And in fact, if I look at the numerical error, it would say that the relative MSE is 7 × 10⁻². So I violate the sparsity assumption. But what compressed sensing theorems tells you is that I recover essentially the best sparse approximation I can make. And it's not that bad. Right? So nothing goes really wrong. Okay. Now I want to suggest a little algorithm which is really silly. So L1 doesn't work. But then you can use a reweighted L1 algorithm, which I'm going to run here. And so I'm going to take this initial solution and try to improve it by solving 3 L1 problems in a row in a way that I won't explain this. I will explain in a minute. And so now we've got, all right, so now I solve 3 L1 problems in a row, and all of a sudden the solution is exact again. So I was able to actually take my solution, solve 3 L1 problems in a row, and then even though I have 2.5, I know that for L1 it's not sufficient. For this algorithm, which is which is an iterative L1 algorithm, then all of a sudden it's sufficient. Okay, so what is this algorithm doing? What is it that I just did? It's very simple. I don't want to spend much time on it. Right? So if you truly have a sparse signals, but somehow the sparsity is a bit too high for L1 to work, then there's a reweighted L1 heuristic that works very well in practice. And what this heuristic does, it does something like this. What we would really want to do is that we would want to minimize the L0 problem, which is just counting the number of coefficients that are not zero, but we can't do it. And a very stupid observation is to say that if X star is a solution to the L0 problems, and if I define weights to be 1 over the amplitudes of the L0 solution, then of course the L0 solution will be the solution to this weighted L1 problem. Of course, I don't know the weights, because to know the weights I need to solve this combinatorially hard problem that I cannot solve. But can I learn these weights? Okay, so this is a very simple reweighted algorithm, which is what you've seen. This L1, reweighted L1, which says, okay, solve L1, get weights, and essentially use this divide by 1 over the absolute values. Take this as a definition of weight. This is going to essentially, basically, it's like discover the big coefficient and then reduce their weight, because they contribute so much to the L1 norm that you want to reduce their weight. So reduce their weight, calculate weights, solve a new L1 problem with those weights, recompute weights, solve a new L1 problems, and so on and so forth. And when you do these 3 times in a row, you've got, even though L1 fails, this algorithm would actually correct the errors and actually recover the sparse signal exactly and without error. Okay, so this is a very simple heuristic that people have found works well in practice, can be used with noisy data, and it's very related to focus, which was introduced about 15 years ago. Okay, so you can really try to boost L1 by having a reweighted scheme that looks something like this. Okay, so maybe I'll skip this. I mean, basically what you're trying, if you analyze what I'm doing, is I'm trying to find a saddle point of nut of this log function. So really what the algorithm tries to find is the local minimum of sum of the log of epsilon plus the absolute value of xi subject to x equals b. And of course, this is minimizing a concave function, which is impossible. But it tries to find a local minimum. And if you have a good initial start, then you'll see that the solution is usually very good. All right, so that's the kind of the first thing I wanted to talk about. And what you can see is like people in my business always plot these curves, which shows that the probability of recovery as a function of sparsity. And so here you have in black you have the L1 curve, which says that as long as for a given number of n is 256, you have about 100 measurements. As long as the sparsity is about 25, you recover the signal 100% of the time. And as it moves over to 45, you never recover it. But if you use this reweighted algorithm, what you can do is you can push this curve so that you can have less sparse signals and still do a good job. Okay. All right. And so when you do this on data, you know, if I were to get my phantom, which we can still not see, and if I were to really acquire it in the Fourier domain by making very few measurements, the minimizing the L1 norm of the gradient, well, you can't see anything, would not work. But if you were to reweight the L1 norm of the gradient, you would do very well. And in fact, you can show that you can actually achieve exact recovery as the number of Fourier coefficients, just 1.2 times the number of pixels where the gradient is not 0. And so you're really at the...
Can I ask a question? Is it purely heuristic or is it
It's heuristic. So it's a very good question, Alain. Even proving that the algorithm converges is already an issue. So it's really heuristic. Yes.
The plot of the gain, presumably your distribution of coefficients were Gaussian or something?
Something like this, right?
If you do Bernoulli?
Yes. So the paper discusses this. If you do Bernoulli, there's no low-hanging fruit, and the gains are far low. This works very well when you discover the big signals and you can discount them in the later stage. There was a talk by Vincent yesterday, which is also a way to debias. You know, the one way to do reprojection, another way is to use this to debias your estimates. Okay. All right. Another thing I want just in my numerical interlude that I just wanted to discuss, going back to some of the questions that were posed, so again, suppose we don't do reweighted L1. So if I just make a signal and the number of equations you give me is too small, so for example 2.5 equations per degrees of freedom, I won't do well. Okay, and so this is going to be illustrated by this plot where I made a signal, and now this signal is sparse, but it's not as sparse as L1 would want it to be. And the thing is, L1 fails, and it doesn't give you a good recovery. Why? Because this signal is not even approximable by a sparse signal. So here it's before I was taking amplitude that were Gaussian, so there were lots of small coefficients. Here they're all plus or minus ones. I don't have enough equations. The sparsity is too high, and therefore, when we talked about this bound in the theorems, x minus xs, this is not small, because I cannot approximate it well by a sparse signal where S is comfortable for L1. I can't do that. Okay, and then in that case, what the theorem says and what the numerics say, and they go n in n, is that the recovery error, this term is not small. This is what we've discussed for like 2 days now. And so that's what you see on the plot. Okay, this term is not small, and here the relative mean squared error is 0.5, which is not good. And the reason is because this signal is not well approximated by a sparse signal. But now suppose that I change the signal to make it I'm going to change it to, I'm going to take half of the entries, keep them the way they were, and the other half, so it's not going to be, the sparsity level will be the same, but the other half of the entries will just shrink them down to 0, so that now I become well approximated by a sparse signal. But the signal is still not sparse, but it's better approximated by a sparse signal, and that's what this is doing. And here is the signal on a log scale. So I have half of the entries at 10 to the minus 2, the other half at 1 in absolute value. The sparsity is the same. I have not changed. All I've done is I've shrunk some of the amplitudes towards 0, so that now this term is smaller, because now I'm well approximated. And then, but the signal is still not sparse, so does L1 work? Theory says it should work, right? And so if I solve the minimization problem, it indeed works, right? So even though I don't have a sparse signal, it doesn't matter, because this approximation error is small. Theory said the error or reconstruction error should be small, and what we see is that, yeah, we do very well. Okay, and so I can check the relative error, and the relative error will be 10 to the minus 4, just very, very accurate, right? Which is essentially what this is. Okay, all right, so I hope that these answer concerns, like, because you cannot imagine the number of talks where people come in, how many measurements, what is the sparsity, is this, blah, 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 and I think Mike also discussed this. It's this, you know, if this is small, then the error will be small. If it's not small, it won't be. And that's as simple as this. Excuse me?
If you rescale a signal, maybe you multiply for a factor very small, you can recover the signal.
If I what? Sorry.
Rescale.
Rescale.
If I rescale the signal?
Yeah. So, for instance, you have a signal that it isn't sparse, but you multiply maybe for 0.001, so that error is very small.
But how do I do this? I mean, what I'm showing you is relative error, really, right? I mean, how do I multiply the signal by something small?
Just rescaling the signal. It's suppose that you have a signal, and before trying to recover it, you can multiply for a factor.
I see. But yeah, I mean, I live in a different world where we try to amplify signals more than.
Yeah.
But I mean, maybe yeah. Okay. Another thing that I just wanted to stop, that a participant asked me, what if you have sparse noise, if you have sparse input noise, impulse noise, like what happens? Okay, so this is my last little thing. So what I'm going to do is I'm going to just make an x0, which is as before, it's a sparse signal, but now I'm going to take some y and completely mess them up. Okay, and that's done in here. I'm going to calculate y, which is a dot x0. There's no surprise here. But then I'm going to look at y. I'm going to take a fraction of the entries of y. I'm going to completely mess them up. Right? This is modeling sparse impulse noise. Okay, so I'm going to do that. But now I say, well, if I recover it classically by the lasso, I'm going to get terrible miss and terrible error. I get something that makes no sense, because the lasso is not designed to deal with impulse noise. It's designed to deal with Gaussian noise. So if I use the lasso to recover the signal, the fact that I corrupted a lot of y's makes the solution have nothing to do with reality. Now, so how do you deal with impulse noise? And that was a question that was posed to me during this lecture. And how do you deal with impulse noise? Well, it's very simple. What you do is you say, well, let's minimize the one norm of x plus the one norm of y minus ax. Right. So what I want to do now is I want to minimize the one norm of x plus the one norm of y minus ax. Okay, and let's see how that goes. So you understand, right? You used your compressed sensing mechanism to send your thing. And then the problem is that some sensor failed, you don't know which ones. And so some values in Y have nothing to do with what they should be, but you have no idea which one. Okay, so that's called impulse noise. But you don't know which entries have been corrupted. Most of the sensors are performing okay, some of them are not, and you have no idea, and you would like still to recover. You have underdetermined equation, 10% of the equations are corrupted, let's say, and you still would like to do well. And so now to do well, we're going to minimize simply the one norm of x plus the one norm of y minus x. Okay, that's what we're going to do. Okay, so let's do that. So if we use, okay, so something is going to run, yeah. All right, and that's perfect again. All right, so here you've seen you have two plots. On the right you have the recovered x, which is exact, and then on the left you have the recovered corruption pattern, the sparse impulse noise, which is also exact. So I could actually detect the locations where we have impulse noise. I could actually correct them and then solve really the L1 problem on what's left, and get the correct answer. Yes.
The rules of A are normalized.
Yes, yes, that's very important. Yes, so I can see that people are really on top of what we're talking about. Okay, so the model of robust compressed sensing, which is studied theoretically, is that we have y equals ax plus e. E is impulse noise, and a is, as usual, our n by n matrix. And the motivation for studying this problem, we want to make compressed sensing robust to dramatic gross corruptions. And so sensor can fail and things can go really wrong. In communication systems, you could have, fading channels and things like that. And so some equations become completely unreliable, but we have no idea which one. And the way we solve this is we say, but look, this is another instance problem. Now we have y equals ax plus e, but e is sparse, x is sparse. So really what I'm looking at is I'm going to look at y equals a times the identity times the sparse vector xe. And so what do? I just minimize the one norm of the right-hand side. And if this matrix is pretty good, then that should work, because that's what we've been studying. And so what you do in general is you minimize the L1 norm of x plus the one norm of x plus the one norm of the sparse vector subject to ax plus e equals y. To address this gentleman's question, you put a lambda that has to do with the normalization of a, absolutely. And of course I can recast this because e is nothing else but y minus ax. I can recast it as this problem. And what we've seen in these lectures is that if this matrix is nice, then things should work, and indeed they do work. And there's lots of papers these days explaining when you can expect perfect recovery from undersample data in the presence of impulse noise. Okay, any questions?
How do you know the lambda parameter?
Okay, so the lambda parameter is going to be adjusted so that this matrix have columns of roughly the same, column norms of roughly the same size. Right?
The one parameter sufficient for this.
Typically, yeah. If A is homogeneous, like it's kind of restricted isometry with eigenvalues 1, for example, you just lambda equals 1. So the parameter has to do with the scale of lambda, like where are the eigenvalues. Okay, so now I think I want to kind of finish this numerics. So I think the main message is, if the signal is not well approximated by a sparse signal, then you cannot expect things to do well. If it is, then it should be fine. Okay, so let's talk about this incoherent sampling theorem now. Okay, so what we've seen in lecture 2 is we've seen these general results where if I take sensing vectors drawn at random from a population, and if I look at the inner product ak.x, and if this population has two properties, the first is that it obeys this isotropic condition, which says that E of A star is the identity. The second is that these vectors are spread. Okay. Then we have seen that if we take fewer than mu times S log n samples, we can't recover a sparse vector. but if we take at least mu times S log n samples, we can. And so my goal today is to try to explain how such a result holds. And I think for this lecture, it would be nice to have the Fourier model in mind, which is we're just measuring, each time we take a measurement, we take a random sinusoid, we just calculate the Fourier coefficients, and we want to understand why is it that from k log n or S log n Fourier coefficients, I can recover a k-sparse signal. Okay. So the goals of this lecture is to give you an idea of the proof techniques, to introduce powerful tools from probability theory, and introduce the golfing scheme, which I like a lot. And so as I said, why don't we just assume that from now on the measurements are obtained by essentially taking the discrete Fourier transform, sampling a few of its rows independently at random, and getting to see a few of its Fourier coefficients. So we have a sparse signal of which we see a few Fourier coefficients. Okay. All right. So what we have seen in lecture 2 is that to actually show exact recovery is almost the same as showing the existence of this dual certificate with the following property. So what we want to show is that the null space of your sensing matrix A is tangent to the L1 ball at the sparse solution, little x. And what we've done last time is we express this geometrically where we derive sufficient conditions for this to happen. And a sufficient condition looks something like this. I'm going to write from now on T would be the support of the solution. It's a set of locations where xi is not 0. And so a dual certificate has the following form. It's orthogonal to the null space of A. Right, so it's pointing in the direction orthogonal to the null space of A. And it needs to be in this cone, all right, because it needs to be tangent to the L1 ball. And what does it mean mathematically? It means that I need to find a vector V, which is orthogonal to the null space of A, which reproduces the sign on T and is less than 1 elsewhere. Right? And if, in addition, the matrix A restricted to the support of the signal has full column rank, then the recovery, the L1 solution will be unique. All right. Okay. So of course, the property that we require that when we restrict A to, so we have our partial Fourier matrix, which is here, we restrict it to a support T, and we want to have full column rank. It makes a lot of sense because if we do not have column rank, full column rank, then recovery by any method whatsoever will not be possible. And why is that? Well, if this matrix does not have full column rank, of course I can find a vector H which is supported on T so that AH equals 0. And then when I move X by any multiple in the direction H by any length, then I get the same data, and of course I can't distinguish X from X plus TH, so I would not know where X is. Okay, so it's actually not a sufficient condition, it's a necessary condition that AT has full column rank, otherwise the solution will not be unique. As soon as you have a solution supported on T, you have it a lot. Okay, so these conditions are almost necessary and sufficient in many ways. Okay. All right, so how do we go about showing that a Fourier matrix, so I have a support, I have a Fourier matrix, but I can only observe a few entries. How do I show that when I restrict this Fourier matrix to a small support, it is actually like an isomorph? It's not rank deficient. So under the theorem hypothesis, what we're going to see is that the matrix AT, this partial Fourier matrix, is actually not only not rank deficient, but very well conditioned as well. In particular, we're going to show that for all vector x supported on T, the norm of AX, properly renormalized, of course, is really equal to the norm of x within a factor 1/2. Okay, so what we're going to show is that for all vectors supported on T, so you give me a fixed set T of cardinality S, so we have a fixed set T of cardinality S. And then I'm going to look at, I'm going to show, and we're going to prove that if m is roughly on the order of s log n, then for all vector x supported on t, so if the support of x, for all vectors x supported on t, then we're going to show that a of x squared minus x squared over m is less than 1/2. Okay, and this is kind of an uncertainty relation if you think about it, because what does it say? It says that I look at the outcome, at the output of the Fourier transform on a small set on a small set, and what the what the lower bound says is that I cannot vanish. Right? So if I'm sparse in time, which means that I'm supported on a sparse subset, I cannot vanish even on a Fourier on a set of frequencies of small cardinality. And how small cardinality do I need? I need roughly s log n. And so it's an uncertainty principle that says that it's a very quantitative and precise uncertainty relationship that says that if I'm sparse in time, and if you give me a random set in the Fourier domain of size roughly s log n, there is no way I can vanish on this set. And not only this, but I can actually accurately predict the fraction of energy that you're going to put on a set of size m. And the fraction of energy you put is simply proportional to the total energy of your signal. Okay, so it says it's a precise uncertainty relationship that quantifies very precisely for sparse signals how much energy can they put on subsets in the frequency domains of size m, and the answer is, well, a fixed fraction of their total power. Okay, and so we use probability, but what we really mean here is that for almost all subsets of cardinality m, that will happen, and there are a few subsets for which it will not happen, but there are not many. So there are three ways of proving this. So there are three ways of proving that a partial DFT matrix is well conditioned. At least I know of three ways, maybe there are others. One way is through methods of free probability and combinatorial ideas, which I will discuss very, very briefly. Another is via a beautiful theorem due to Mark Rudolphson that I call the Rudolphson selection theorem, which is really a way of getting law of large numbers for matrix valued random variables. And the third way, which is by far the most elegant, is by something called the operator Bernstein inequality, which I will spend most of the lecture discussing. So how do you prove that such a matrix is well conditioned? Well, to prove that my matrix A star T AT is well conditioned, well, I want to show that all of its eigenvalues are between m over 2 and 3m over 2. So if I rescale the matrix by 1 over m, I want to show that A star T AT does not deviate from the identity by a very large amount. So I would want to show that the matrix H that you see on top has all of its eigenvalues less than 1/2. Okay, the eigenvalues should be centered around 0 because the expected value of, well, it follows from the isotropic condition that the expected value of A star T AT 1 over m is simply the identity over T. That's the isotropic condition. And so what I want to show is that I want to show that this matrix actually does not deviate very much from its expectation. On average, it gives me the identity, but I want to show that it does not deviate from the identity very much. So how do you do this? Well, the way you could do this is you'd say, all right, so I want to understand the behavior of the largest eigenvalue of this matrix H. I want to show that it's small. Well, you can follow essentially ideas that were pioneered by Eugene Wigner, saying, I don't know how to do this really, because this matrix is very complicated. It's a matrix I get by taking a full DFT matrix, which is unitary. I sample a few rows. I take an arbitrary subset, and I've got a sub-Fourier matrix, and I want to show that this matrix is well conditioned. And so the first idea that comes to mind is to use what is called like a moment method, where you say, all right, I'm going to raise this matrix H at a very large power. And of course, the trace of H to an even power would be the sum of its eigenvalues raised at this even power. And the reason we raise this as, or like Wigner raises it at a large power, is because, of course, in this sum, everything will be dominated by the largest eigenvalue. And so now the trace of H2k is something that you can compute. And so the idea of the combinatorial approach is to actually take this matrix H, this partial Fourier matrix, raise it at a large, subtract the identity, raise it at a large power, take the expected value of the trace, and try to bound this quantity. And if you can bound this quantity, then of course you will bound the largest eigenvalue. You will get an upper bound on the value of the largest eigenvalue. And Eugene Wigner did this for Gaussian random matrices, of course. And that's one way you can actually find the limit of the largest eigenvalue of a Gaussian matrix. Now the problem is, what's true for IID matrices, which is that we've got lots of independence in this matrix, is absolutely less clear in this situation. And so when you look at this combinatorial expression of raising this sub-Fourier matrix at the large power, then you're going to run into combinatorial issues that involve statistics of various paths in the plane. These are very complicated variants of Dix path that people who know lots about random matrices know about. And so we cannot invoke standard moment calculation method that were done for matrices with IID entries. You have to do the combinatorics by hand. It gets complicated. But what's remarkable, what's interesting about this answer is at the end of the day, if you're very careful about how you bound the various terms, you get fairly sharp answers. And that's really something that these simple methods, they tend, once you can carry them through, they give sharp answers. I mean, they actually give you very sharp constants. And we know this because we know that for Gaussian matrices, they will tell you exactly the location of the largest eigenvalue and things like this. So they give really sharp answers. They're hard to develop in this case, in these problems where we have structured measurements, but they can be carried through, and that's what we did with Justin and Terence. But there's another way of looking at this, which there's a second way by Ruderson, which I'll skip. There's another way which was introduced in the community not long ago, which is by something. It's a big hammer, and it's a hammer that we've been looking for. So everybody knows, I think everybody knows the Bernstein inequality for real-valued random variable. It's a large deviation inequality that says the following, that if I take xi to be independent real-valued random variables with mean 0, with variance bounded by sigma I squared, and let's assume that these random variables are also bounded in absolute value, then we know how to bound the sum of these absolute values. We have this famous Bernstein inequality that takes that the probability that the absolute value of the sum is greater than t is less than exponential minus t squared divided by 2 times the sum of the variances plus 2 times the maximum value of xi times t over 3. Right? So you have typically, if c is small, you have a Gaussian-like tail. If c is large, you have an exponential-like tail. So you have either the Gaussian or Poisson behavior that we all know. Okay, so this inequality is well known. It's very useful. We use it all the time. Everybody uses it all the time, and so on. But what about matrices? The remarkable thing is that there is something exactly similar for matrices. And what does this theorem says? It's due to Alswede and Winter. And they actually worked out, it's funny, this theorem, which I find so useful and so central, is actually in an appendix on a paper on quantum information theory. And it's a kind of a tool they prove in passing to do what they want. But to me, this is a jewel. And what does this result say? It says we take xi to be independent n by n symmetric Hermitian. So now we have xi's, which are independent symmetric matrix-valued random variables. We're going to make the similar assumption as the Bernstein inequality in the real valued case. We're going to assume that these random variables, these matrices have mean 0. We're going to assume that we can bound their variance. So I have an upper bound on the norm of the expected value of xi squared. And I'm going to assume that these matrices are bounded in norms. There's a really, really useful result is this. which is that when I look at the probability that the spectral norm of the sum of these variables exceeds the threshold t, is exactly what you get in the real case. It's 2 times the dimension of your matrix times exactly the same factor, where v simply is the sum of the variances. So if n equals 1, it's exactly what you have above. But of course, it applies to matrices, and it's a very useful inequality that bounds the spectral norm of a sum of independent random variables once you know that they are bounded and when they have a variant that is controlled. Excuse me? It's a usual norm of a matrix, the largest singular value.
When is the result? When is the result?
2002. Okay. All right. There is an improvement due to Oliveira and Trop, where you can actually sharpen this result. Where I think the sharpening comes from the fact that you can the upper bound you need here is simply the bound of the sum of the x. So you can put the sum inside if you want, which is also very useful. Okay, so I stated the theorem because it's simpler to state it for symmetric Hermitian matrices, but it extends to non-symmetric matrices. And what you just do in this case is you just say you're going to put a bound on the variance, but the variance now you have a non-symmetric matrix is going to be the maximum of the norm of xi transpose or xi transpose xi. So you take whatever is the maximum, and that's your sigma I, and the results apply as is. Except that now, instead of 2n, you have 2 times the sum of the dimensions. Okay, that's a very beautiful result. And with this result, the fact that Fourier matrices are sub-Fourier matrices are well conditioned is a triviality. And why is it a triviality? Because now the rows of A, we have always called them AK, so the rows of A are so that's my matrix A, right? So this is a sinusoid at a frequency omega k. Right, so when I look at a row of AK, I see exponential I minus t pi omega kt over n. And of course, A star A simply is the sum over k of AK star. Okay, and so when I restrict this Fourier matrix to a subset of column T, what I'm doing is I'm essentially restricting the sinusoids to a subset of input capital T. Okay, and so A star T AT is the sum of UK star, where UK simply is a restriction of your sinusoid to the values of T which are in your support. All right, and now we say, well, what is A star T AT minus its expectation, which is simply m times the identity? Well, it's a sum of random variables xk, where xk is simply, by definition, UK star minus it. But now I can apply, because now since I'm sampling those frequencies independently at random, these xk's are independent matrices. In fact, they are very simple matrices. They are a rank 1 matrix minus the identity. And so now I have to bound the spectral norm of the sum of these xk's, but I can use this. And so let's do this. First of all, they are centered. The expected value of xk is 0. I can compute the variance. I can take xk, calculate its second moment, and when I do this, I'm going to use that I'm dealing with sinusoids. And when I'm dealing with sinusoids, I get this simple expression. I get s minus 2 times UK star plus the identity. So in particular, if I were to take the expectation of xk squared, well, the expectation of UK star, we already know that it's the identity, right? Because that's the isotropy property, the fact that I'm sampling from a unitary transformation. So the expected value of xk star, the expected value of this is going to be s minus 2 times the identity plus the identity. So on average, E of xk squared is just s minus 1 times the identity, and therefore the variance is less than s minus 1. Finally, I can control, of course, the spectral norm of each of these xk, because xk is a rank 1 perturbation of the identity, so there's nothing simpler to bound, so it's going to be essentially the maximum of the the norm of the uk squared, which is s, right, minus 1, so it's less than s. So I can apply everything in the theorem because they have mean 0, I control their variance, I control their spectral norm, and so I just apply this, and you just apply the operator Bernstein, and what it gives you is that sub-Fourier matrices are very well conditioned since the probability that they deviate in the spectral norm from the identity by more than t is going to be 2 times the dimension, which is here is an S by S matrix. So you put these results together, minus exponential m over 2s times this Bernstein-like factor, and so we have a large deviation bound. And so we see that when when m is a bit bigger than s, this is going to be very small. And so that says that sub-Fourier matrices are very well conditioned. All right. So what used to take 20 pages of combinatorics takes half a page. Okay. All right. So this is one way. I mean, of course, what we have done in here is we have shown that AT has full column rank, and we've shown that sub-Fourier matrices are well conditioned, but we have not constructed the dual certificate. So to construct dual certificates, we can use the ID that we used for Gaussian on yesterday morning, and try to construct it this way. And that's what we did with Justin and Terence. And so we could try to take our guess of dual certificate, the one that essentially does what we want. It has minimum M2 norm. And when you do this, we're going to use a Neumann series to expand A star T AT inverse. Now we know that it's well conditioned, so we have no problem inverting it. Okay, so we're going to expand this as a Neumann series as the sum of this H, which are these deviations from between A star A and the identity. Okay, and so we're going to hit this Neumann series with A star AT. And so what we're going to do is what our dual certificate, what it does, it takes this form. It's a sum of VJs where each VJ is a term in this Neumann series, which looks something like this. Okay. And now how do you bound V on T complement to show that it's less than 1? Well, you take each term and you try to bound them individually. And how do you do this? By the moment method. Right? So you're going to take each term, raise them at a large power, try to find, again, combinatorics show up, try to find a good bound on what you get over here, and then assemble the pieces and prove that indeed V is small. Okay? And I think everything is complicated because the randomness, which comes from sampling the rows of the Fourier transform, is in every term. It's in A, it's in here, it's in here. There's nothing that decouples that makes things easy. And so that's why this approach, this combinatorial approach, is a bit tedious. But again, it gives good answers. Okay, so what I would like to discuss now is another solution to construct a dual certificate, which is essentially due to David Gross, and I think it's a very clear and beautiful idea. So first of all, the first thing that we may think about is to kind of relax the condition for dual certification, and so we've seen that to be a dual certificate, to have actually this tangent property, I need to reproduce the sign on the support, I need to be less than 1 outside of the support, and I need AT to be has full column rank, to be non-singular. And you can actually prove that X will be the unique optimal solution if you have a slightly different set of conditions. what you want to find is you want to find a set V, which is also orthogonal to the null space of A. But now the innovation here is that you don't really need to match the sign precisely. It's enough to come close to the sign. And so we're going to require that Vt is equal to the sine of xt plus a perturbation. I don't have to reproduce the sign exactly, and that's a novelty here, as long as this perturbation is small. So I need to match the sign approximately. So as if I can match the sign up to an error which in 2 norm is less than 1/8, I'm fine. But of course, because now I relax the sign matching condition, I'm going to put stronger condition on everything else. And the condition I'm going to put on everything else is now outside of the support. I don't want to be less than 1. I want to be quite a bit less than 1. I want to be less than 1/2. And outside, and I want to, AT before needed to have only full column rank. Now I just want to know that it's well conditioned, but this we already know. Okay. All right. So this is, if you can prove that such a V exists, then it would show that X is a unique solution by simple calculations. Right? So the idea here is simple. It's a bit stringent to require that we match exactly the sign. So why don't we just relax this requirement a little bit? Okay, now here's David's wonderful scheme for constructing a dual certificate. What you're going to do is, I'm giving you measurements, and you're going to assemble them in batches. Okay, so what David is doing essentially is going to try to come back to this case that we studied yesterday, this Gaussian case where everything is independent and the analysis is so simple. So I give you a bunch of measurements. Each time I give you a Fourier coefficient, which is randomly sampled. And so I'm going to give you a matrix A, which looks like this. And you're going to decompose it into batches. You're going to take the first m measurements, m1 measurement, and you're going to call this a first submatrix A1. You're going to take the second batch, and you're going to call this A2. You're going to take the third batch, and you're going to call A3. The fourth batch, and you're going to call A4, and et cetera, et cetera. Right, so we're going to partition the rows of A into L row blocks such that these are the first measurement, these are the next ones, et cetera, et cetera. Right, so I do this decomposition. And then it's going to construct a dual certificate, an approximate dual certificate in the sense that we've just discussed, recursively. And so it's going to start by saying, initially my guess is V equals 0. But inductively, what you define is you're going to update your previous guess. And what you're going to do is you're going to say, the formula is 1 over the number of rows in batch number I times AI star AI restricted to T times what the target, the sine of xt, minus what you had before, plus your previous guess. Okay, so that's a golfing scheme. Right? You divide this into batches, and then inductively you update. You take the first batch to construct a guess of a dual certificate, and then it's not a good guess. So what do? You take the second batch of measurement to improve this guess. It's still not good. You take the third batch to improve this guess until you hopefully converge to something that would obey the conditions for dual certification. Okay. All right, so let's use the first measurement to construct a guess, and then let's try to improve this guess at each iteration. The key point in this construction is that because these batches of rows are independent from each other, what this scheme does, it completely decouples the randomness you have in the argument from the randomness you have here, because this depends on the first batches up to I minus 1. This depends on the ith batch. But because all of these batches are independent, everything decouples. And so this is, as far as this matrix is concerned, this is a fixed input. Okay, and so the key point in this construction is that it decouples everything, which means that this matrix and vi minus 1 are independent, which is what is going to make everything work. And the analysis will be simple because of this, because basically we're almost in the case that we studied yesterday. All right. Okay, so this is a construction. So let me try to explain why this construction makes sense. The first, if you look at the beginning, V0 is 0. So what is V1? Right, so this is, we have the formula here, which I copied over. So what is V1? V1 is going to be 1 over M1 times A star 1, A1t times the sine of xt, because V0 is 0. So A1 V1 is simply 1 over M1 times A1 star A1t times the sine of x. And V1 is not such a bad guess for what a dual certificate might be, because it's certainly orthogonal to the null space of A. It's of the form A1 star times something, so it's in the row space of my matrix A, since it's in the row space of A1, so it's orthogonal to the null space of A, so that's good. On average, it gives me the sign, so when I look at the expected value of V1, it's going to be the expected value of 1 over M1 times A1 star A1t times the sine of xt. But the expected value of this is simply the projection onto t, because the expected value of A star A is the identity. So this is the projection onto the set t of the sign vector. So it's actually giving me, on average, the sign and 0 elsewhere, which is perfect. That's what I want. So on average, it does the right thing. And so it means it says in some sense that as a first step, it's not a bad step because it goes in the right direction. On average, it gives me what I want. It's in the row space, so it's orthogonal to the null space. And so it gives what I want. Now let's look at the update. The update says that now sorry, I made a mistake when I copied this. So the update should be V2 equals V1 plus 1 over M2, the sine of xt minus V1. So I'm missing V1. Right? Because really, what the next step should be, you should try not to approximate the sign, but the difference between the sign and my first guess. Okay, so the next step should really approximate the difference between my guess and my target. Okay, and that's exactly what the second step is doing by the same reasons. Take V1 and then use a measurement to refine your measurement by approximating the difference between the target and what should be V1 here. Okay? And that's why Gross calls this the golfing scheme, because you have a target, which is a sign vector. It's a weird name. A lot of people ask me why it's called the golfing scheme. But you start with V0 equals 0, and then you're going to take a shot and arrive at V1. Your target is somewhere here. Okay? And so you took a shot, and now you're going to try to kind of bring V1 closer to the target by taking another shot. All right, that's V2. And then you're going to try to get closer to the target by taking another shot. That's V3. Right. And that's kind of like a golfer trying to put the ball in the hole. If you do we have people from numerical analysis? It looks very much like Gauss Seidel for actually constructing our dual certificate. Like our certificate is this, and it seems like an iterative method to actually construct this guy, except that it's a bit clever because we partition it this way. That's how you maintain independence, right? So it's essentially a funny version of Gauss Seidel to actually construct the dual certificate that we proposed. Okay. All right. So now maybe I will try to explain why this works and why you can get what you want. Okay, so the so I'm going to try to write somewhere. So by construction, of course, this dual certificate is going to be in the null space, orthogonal to the null space of A, since it's a linear combination of the rows of A, so it's in the row space of A, so it's going to be in the null space of A. All right, so it is in the null space of A. Now we need to show that it's actually close to the sign, so that actually this golfing scheme is going to bring me close to the sign, and that the norm outside of the support is less than 1/2. Okay, all right. So maybe to go a bit more slowly, I will just write a few things on the board. So so we have the expression for the golfing scheme, okay, which is at the top. So it's this inductive process. And so the first thing we need to understand is QIT. What is it? It's the difference between my target, the sign of xt, and my guess, which is the guess at iteration I of the golfing scheme, VIT. Okay, so that after the process terminates QLT, which is as I'm running out of measurements, as I'm running out of blocks, the golfing scheme declares that the last update is the dual certificate, and so it's going to be DLT, it's going to be exactly what I want, delta T. The difference between sin xt and the value of v. Okay, so now because of the way the dual scheme is constructed, people familiar with numerical analysis will immediately see that QIT is nothing else. There's a recurrence relation that says that QIT is nothing else but the identity minus AI star AIT times QI minus 1T. Right, and that's the way we update the residuals in Gauss-Seidel. But that's very good. And why is it very good? Because we know that this matrix is a contraction. If I have enough samples, then these blocks, restricted to proper columns, of course, are nearly isometric. And so therefore, I know that this matrix has all of its eigenvalues between -1 and 1/2. And therefore, at each iteration, the error of QIT is half what it used to be. And so each time I go through this golfing scheme, when I go through this thing, each time I decrease the distance with the target by a factor 1/2. So if I take log s, right, and so what is Q0? So this gives me that QIT is less than 2 to the minus I times the norm of Q0, but Q0 is simply V0 at the beginning, so it's the norm of the sign vector, which is square root of s. And so after L steps, I'm going to have an error, which is 2 to the minus L times square root of s. So if L is logarithmic in s, then I'm very close to the sign vector. Right? So what we see from the golfing scheme is that after log iterations, I'm going to have no problem obeying this condition, because each time the error decreases by a constant amount. Okay, so that's the first step. The first ingredient of the golfing scheme is saying we know that these matrices are well conditioned. Therefore, I have geometric convergence towards the sign pattern that I'm trying to reproduce. Okay. And that's kind of what explains here. Note that in general, you don't need to actually do this. You actually need a weaker requirement that I don't really need to have actually that this matrix in spectral norm is less than 1/2. Because all I care about is really that on a fixed vector, right, all I care about is that I don't really care that all the eigenvalues of this are between less than 1/2 in absolute value. All I care about is this. And this is a much weaker requirement because I ask that on a fixed input, I decrease by 1/2. And so you don't need actually to show the full concentration of all the eigenvalues. You can actually, as long as this matrix is reducing the size of Q, and because Qi minus 1 and Ai are independent, on a fixed input, as long as you do this, it's fine. Okay, now we have the last conditions to check, and the last condition to check is that V is small outside of the support of the support set T. Okay, and so now I can sum the V's together. So the expression for V, which is when the process terminates in terms of these Q's, is the sum of I equals 1 through L of 1 over Mi times Ai star Ait times Qi minus 1t. And now I want to show that this vector is small on T complement. Okay, so I'm going to use a very naive bound. I'm going to say that the norm of V on T complement in infinity is going to be less than the sum of these infinity norms. Okay, and therefore all I need to control is the infinity norm of each term. But that's where this decoupling helps so much, because this is, as far as this is concerned, this is fixed. And so what is this term? It's a random sum. So maybe I will right. So I'm writing exactly what I wrote on the board. V is this vector. So for each I, each term in the series is of this form. But if you hold Qi constant, because you condition on the history up till I minus 1, then this is a fixed vector. Condition on the history, this is fixed, and then you apply a random matrix to it. But this random matrix is very simple, because this random matrix is really a sum of rank 1 matrices. Okay, so AI star T is still AI is a sum of K in my batch I in batch I of AK okay, so that's a random sum. So now I'm hitting this random sum against a fixed vector, which I'm going to call Q for simplicity. So I have a random vector sum. Now I say, what is the T's component of this random sum? Well, I have a random sum of independent random variables now. I can apply Bernstein inequality. I'm in a completely classical setting, right? Because I have decoupled the randomness in here from the randomness is here. So now I have a purely random sum. I can compute the mean, the variance, the maximum value that this can take, and apply Bernstein inequality. And for each term in the series, I will be able to bound its size just by classical ideas, by Bernstein inequality. Right? So for each entry, what I'm saying is for each entry of this vector, each entry of this vector is a random sum of IID random variable of independent variables. I can apply in Bernstein the classical Bernstein equality. I don't even have to be fancy to bound each term, and I can show that VT complement is small. And so that's the idea of the golfing scheme in a nutshell. I find it very, very elegant, and the version I present here will not be able to give you that you can recover from S log n Fourier coefficients. You would need S log n squared, but there are variations that would allow you to remove this extra log factor. Okay, so the golfing scheme is very useful. It's something that the community has recognized as being an important tool. We applied it ourselves to matrix completion problems, to robust recovery problems. So the problem that I mentioned at the beginning of recovering a signal from compressive samples corrupted by noise can be tackled by these techniques. It's applied to RPCA, which I'll discuss tomorrow. It's a very useful tool in general. Okay, I'm running out of time. I had a numerical interlude at the beginning. I had the mathematical interlude, which was to actually prove, which is not very hard, this this Alswede-Winter operator Bernstein inequality. The proof is not very difficult. It relies on a key inequality from statistical mechanics called the Golden-Thomson inequality. And so the proof, once you know this inequality, is not difficult because essentially the proof for real valued random variables. And this inequality is very beautiful. It said that the trace of the exponential of a sum of two matrices is less than the trace of the exponential of A times the exponential of B, which is this inequality that is allowing us to bypass all the combinatorics, because all the combinatorics is in there. Okay, of course, if A and B commute, that's not a surprise. But when they don't commute, this is a deep fact of life. Just for simplicity, how many people are familiar with the Alswede-Winter result? Very few. Okay. All right. I think it's beautiful. And so the proof is not difficult. But the key step in the proof is this remarkable inequality from statistical mechanics. Because basically then you write your random sum as, you go through the moment calculation, the exponential t of your sum. And then you want to kind of, when we have independent sum, exponential of a sum becomes product of exponentials. And so we can treat them individually. When we have matrices, we can't do this. But if we have this, we can. Because then that's where you restore. Okay. And so you can use an induction argument. And that's really neat. And it avoids so much combinatorics. In fact, the proof of this inequality is not combinatorial. I mean, there are proofs of this inequality which do not go through combinatorics. Okay, the summary, we can recover a vector from S-log and measurements. It uses what I consider to be sophisticated ideas from probability theory. Of course, I just prove only like the simplest result that if you're sparse, I can recover you. We did not address the case of noise. We did not address the case of non-sparse signals. Of course, in this case, the proofs are much more involved. And to discuss noise, we'll do this afternoon. Thank you.
Question. Can you just go back to this operator valued Bernstein inequality? So you have the dimension n in front of the exponent. So in a way, this is not really a dimension-free concentration inequality. No. So my question is, are there neat simple bounds for the expectation of the spectral norm of the sum of xi's? Because if you would have that, in a way, you could just use Tarragon's inequality. It would give it exactly the same without the 2n. But you would concentrate around the expectation. Mm-hmm. And so in a way, what this says is that the expectation has exactly the size root log n, and the price to pay that you're not above the expectation of the inequality is that you put the 2n in front. But if you had a simple bound for the spectral norm of that sum, it would follow the Tarragon 10 years before this reference. It seems to me that bounding the expectation of the spectral norm should be much easier problem.
But if you look at the way people did these things before, I agree with you in principle. I think that the community of geometric functional analysis realized very early that the whole problem here is to actually bound the expectation. And that's why Ruderson, that's what motivated the work by Ruderson. So Ruderson was actually introduced, Bourgain, and then it was refined by Ruderson, introduced this very powerful technique based on non-commutative Keating inequality, trying to actually give tools to actually bound the expectation. Because once you're absolutely right, once you bound the expectation, then by Talleyrand you usually have concentration, absolutely. But how do you bound the expected value of that's the critical part, and that's what this does for you.
Right, so was this not done before Alswede-Winter or something? I mean, I'm just curious. Is this...
Not to the best of my knowledge. Alswede is a very, David Gross, whom I know quite a bit, said that one of these two, I don't know which one, maybe it's Winter, maybe it's Alswede. They are very accomplished people, and they consider this to be their very beautiful results of theirs. I think your point is really well taken. I think that if you look at Witterson's papers on isotropic, the isotropic paper, you'll see that Witterson spent all of his proof actually developing a bound for the expected value of this norm. And then he says, of course by Talleyrand I can get concentration around this, but how do you bound the expected value? That's a big problem. Right? And that's what this does.
I have a naive question. What goes wrong if I sample uniformly from the Fourier matrix? So I don't sample randomly.
What does it mean to sample uniformly?
I'm just taking frequencies which are apart, equal sized.
Aliasing.
Sorry?
Aliasing.
Yeah. So then I have perfectly conditioned submatrix.
Yeah, but you have aliasing. You cannot recover S-bar signals anymore. You have what Mike discussed. You have big aliasing problems. Like if you sample on a structured lattice, I can construct easily. We saw examples in lecture 2, right? Let me just try to go back in lecture 2, which we had this, I think, thing that would answer your question. Suppose this is my sparse signal.
Yep.
And you sample uniformly. 1, 2, 3, 4. You see 0 all the time.
But there is small probability that this happens because this is one specific example where it happens. So there is still some chance that I fail, as there is chance in the random sampling method.
Yeah. So if you're
very pragmatic, if you say why I should be randomizing algorithms in case I don't know anything about my true signal, why not just uniformly sample and hope for the best?
I agree. I mean, there are several views of the world. There are people who are willing to assume. I'm not really willing to assume that I can put a stochastic model on MR images that have random supports in some domain that I'm not sure about. I'm not comfortable with that. Okay? But if you're willing to take this, saying, I'm willing to admit that the signal has a random support, maybe some random signs to help me, maybe some random amplitudes. You're willing to put a lot, to take a lot of the randomness that we have in the sensing mechanism and to put it on the signal side, then you can have results for deterministic matrices because you put the randomness somewhere else. What compressed sensing says, and I think Mike, is that we make no randomness assumption about the signal. The signal is what it is. If nature decided to cook a signal, that's what it decided to cook, and it did not throw dice to do it.
Okay.
But you're right. You have a dual point of view. You're absolutely right. You have a dual point of view, which is maybe I have a fixed matrix, and maybe if I want to say something clever, maybe I have to randomize the input. Okay? And then we go back to lecture 1, where in lecture 1 I said that the point of view that we have in compressed sensing actually informs your point of view tremendously, since I can essentially dualize every proof and show that if I can do random A fix X, I can do fix X A random X, roughly. Right? So that's why even if you don't buy the compressed sensing slogan, you can use the techniques that you see to actually modify them and apply them to exactly your setting where you have a random input and a fixed matrix A. And a lot of things will stay the same.
Do people use this in practice? Right?
In practice to do...
I mean, you mentioned that these things are going to hardware implementation, and there you can save a lot if you don't...
But what's the beautiful thing about hardware implementation is I can actually randomize my sensing device. That's why I think it's an exciting field. I can go to an engineer and say, why don't you load in this buffer a random sequence of plus and minus 1 so that we're actually measuring random samples of the signal. I can make a device. I can tweak an ADC, an analog to digital converter, so that instead of sampling uniformly in time, it samples non-uniformly in time at random location. I can do this. I just mess up the clock.
Okay, that's a good one.
Right? So we can. What's exciting about this field is that we can actually design systems that take advantage of randomness. Right. So an ADC sampler essentially has a voltage, and each time the voltage will cross a line, boom, it decides to sample. But I can mess up the clock so that instead of having this voltage cross the line at at a equispaced interval, it actually crosses the line at random locations, and then I have an ADC with very little work that would sample non-uniformly in time. And then when I have high frequency spectrum, I can see that this works much better because I don't have these problems, these
So
aliasing
it's
problems.
observed that it works better.
Yes. It's less subject to signals assumption. In the theory of computer science, you have the same thing, which is, are you randomizing the algorithm or are you randomizing the input? You know? And that's here we're randomizing the algorithm, not the input.
Right, yes, one more
Okay, I
question.
have a small question. In a golfing scheme, when we reach the last block, do we go back to first block and repeat again?
No, because then you would introduce dependence, so that makes the analysis impossible again, and the last block is good enough. Yeah, it's like the golfing scheme is, take the first entries to take your best guess, then you use them to make your best guess, so they're not useful anymore. But we could try to do something smarter. The thing is, like, if you go back to the first block, then of course the input to the first block depends on the first block. Since it depends on history, you will destroy the independence. That will make things difficult.
So, we'll reconvene at 2 o'clock, but could we thank Emmanuel for this noise talk?